Hey, welcome to this lecture where we're going to talk about, we're going to do an introduction to science and equations. And this is just a short lecture to get us started, primarily because I want to get you thinking about measurements, equations, and the relationship between variables and properties before actually introducing physics equations and variables themselves. So let's talk measurement. In order to understand the characteristics of the world around us, we need to take measurements and analyze the results. We can't know how big something is unless we measure its size or compare it to something else. So let's take my water bottle. My water bottle is the length of my hand plus a half. So 1.5 of my hand tall. That's my water bottle. That isn't really helpful for you if you don't know how long my hand is. I could also tell you my hand is a tiny bit shorter than a TI-84 graphing calculator, but that only helps if you have one of those calculators. Telling you the size of the water bottle based on another object is only helpful if there's a standard size of that object. Hands obviously vary in size. And the calculator does have a standard size, but it isn't something common enough that people could use it to measure the size of things. But if instead I compare the size of my hand to a ruler, and I tell you that my hand is 7 inches tall, then you can figure out how tall the water bottle is and compare it to anything else you have around. So let's figure out how tall my water bottle is in inches, not hands. We know that my hand is 7 inches tall, and the water bottle is 1.5 of my hands tall. So let's bring out our ruler. One of my hands is 7 inches, and half of 7 is 3.5. So half of my hand is 3.5 inches. And we can combine those to find the height of my water bottle. So 3.5 inches plus 7 inches is 11.5 inches. That is how tall my water bottle is. This was meant to show the process of measuring an object and the value of using a standard measurement. We can't do much if I say this is 4 hands tall and we don't know whose hands we're talking about. But if we compare the hand or the object we're measuring, skipping some steps, to a standard measuring tool like a ruler or a meter stick, then we can say that the object is instead 28 inches tall. That information allows us to compare the sizes of any object to a standard reference. Like we can compare my water bottle to your water bottle. Or something more relevant to the topic of interest, but we're on water bottles right now. So first off, though, we use standardized measurements to observe and record characteristics of the world around us in order to compare things so that we can better understand them. So we can see that your water bottle here is taller than mine. And with something like a water bottle, another useful comparison could be how much water they hold or the volume. And that is usually listed for us on the water bottle, but there are also ways to determine that if they aren't. My water bottle, for example, holds 32 ounces. What about yours? Now let's talk about the scientific process. I know there's a lot of words on this slide. Don't worry about it. I'm going to read most of them anyway. So first, you observe the characteristics of an object or phenomenon, like we did with the water bottle. We observed its height. And then you determine something you might want to know about that object or phenomenon. How big is it? What happens to this characteristic when I change this other characteristic? Make a prediction about the next step is to make a prediction about the object or the phenomenon. I think if I throw this ball harder, it will travel farther. That's my prediction about the phenomenon of throwing a ball. The next step is to plan and execute an experiment to test your prediction. How will you determine how hard a ball is thrown? How about how far it travels? And what would the results need to be to prove your prediction right or wrong? Then, after you've thought through those things and gotten your results, you analyze the results of your experiment. Did they match what you expected? Did the ball travel farther when it was thrown harder? Or was there a point where it wouldn't travel any farther? Next step, our last step really, is to determine if your results point to a generalizable rule, like the harder someone throws a ball, the farther it will travel. And this is a made up situation to show you the process without giving you answers to future questions. So no, there probably is not a limit to how far the ball travels if a person throws it hard. But this is the example that I could think of at the top of my head. So it's an example we're working with. In physics, we can actually simplify these situations even more. What about throwing a ball harder makes that ball travel faster? And that's something we will talk about in another lecture, but it's something to think about. So, physics itself is a foundational science where we study how and why objects move and interact the ways that they do, from stars and planets and galaxies down to molecules and particles. We, in this class, will primarily be working at a scale between those two things. So instead of a planet, it would be a ball or a person. But the physics is mostly the same at all of those scales. And we can talk about planets and stars if folks want later on in the quarter. Although, I mean, we could also maybe talk about molecules and particles too. That's an option. So let's talk equations now. Because in our study of physics and the motion of objects, we will be using equations. Equations help us keep track of how different variables or characteristics relate to each other. If we go back to the water bottle example, often the taller a water bottle is, the more water it can hold. But we also know that isn't always true. Maybe the water bottle is tall but skinny, and then it's not going to hold as much water. We could adjust our statement to be assuming a constant width, as in the water bottle doesn't get skinnier, it stays the same size, but it gets taller. Then a taller water bottle would be able to hold more water. So let's look at some other examples. And here's an equation to base it off of. We have A plus B equals C. So A, B, and C here are our variables or characteristics. So although this equation does not directly translate to what I was just saying about like the height of a water bottle, the variables are the same kind of thing. So like the height of a water bottle, that's a variable. The width of a water bottle, also a variable, and how much water it can hold. All of those are variables. So back to this equation. Looking at this, we can see that if A, whatever it is, got bigger without B changing at all, then C would also get bigger. Or if A stays the same and B gets smaller, then C will also get smaller. That's what this equation is telling us. And this is why equations are so valuable. They show us how variables relate to each other and how changing one may change the others. Here are some other equations. The more ways that variables may relate to each other. We have the addition one we already talked about, but we have subtraction instead. And then we have multiplication. I didn't include the multiplication symbol because frequently we'll leave that out, but that's what this is saying. It's saying A times B equals C. And then division, A divided by B equals C. So I want you to think about how these equations can describe real world relationships. And I'll give you a couple of examples to work with first. So first, back to our A plus B equals C. Let's define these variables into something in the real world. So let's say A is the money I start with. And then we're adding B. Say that is the amount of money I'm paid in my paycheck. So the money I start with plus the amount I'm paid is equal to the money I end up with. Okay, that's a simple way to explain a relationship using this equation. Now let's try the subtraction version of the equation. A minus B equals C. So here A is still going to be the money I start with, right? But my paycheck is not taken away from me, it's given to me. So let's pick something else for that. Let's say B is the cost of something, the amount something costs. So A is the money I start with, and then I subtract how much something costs, and C gives me how much money I end up with. So I want you to be thinking about what relationships might be described by simple equations. And make sure you complete your post-lecture assignment. Like I said, very short lecture for this. We're just getting started. But I don't want you to be overwhelmed by equations, but they will be really important. So we're starting out with just getting a feel for them.